Hi, today we're going to learn all about the mole and how it relates to the number of particles in any kind of substance. So take a moment to answer these questions. You can just do it kind of in your head or just write down your responses 1 through 5 on your paper and then come back and see the answers. Be sure to pause. Alright, let's take a look. So again, this is just kind of getting into the idea of what it means to be different types of particles. So we're looking to define what a mole is in Avogadro's constant. This is given to you on your reference sheet. It's just another equality for you to use in order to do some chemistry stuff. So what is a mole? No, that's not the sound they make. A mole is just so many particles. It's an enormous amount of particles. That doesn't seem to make much sense, but that's okay. Don't worry. Just like when you know of a dozen equals 12, a mole, which this is the abbreviation MOL, equals so many particles. Now 1 mole equals the atomic weight of an element. We also call that the molar mass. And for oxygen, if we just have 1 oxygen, 1 mole equals 15.999 grams. That's an equality we can use to determine how much so many particles weighs. And that's what we'll be using this for. So the idea is that 1 mole is equal to the molar mass, which is equal to the average atomic weight of any element. So we're going to need a periodic table going forward. So the mole map is just meant to give you a relationship of how we can go from grams and convert to moles. We would use the formula mass, i.e. the molar mass. If we wanted to go to moles to different particles being atoms, molecules, or the ionic equivalency of molecules called formula units, we would use Avogadro's number, which is the number of particles in 1 mole. I'll show you how to use these for every type of example, so you can just follow the mold in order to determine these going forward. Alright, so let's take a look at some of these examples here. So I start off with my known, 10 grams of aluminum. And I want to know, how many moles of aluminum that would be. So again, like before, I start off with my units. There are so many grams of aluminum, because that's what I start off with. Whatever's on top goes on the bottom. And I can relate that to moles of that substance. And because this unit up here on the top matches the unit I'm trying to find, good. So I have 1 mole, and I look at my periodic table and see that it's 26.98 grams. Let's always stick with just 2 decimal places. It makes it easy to always have the same values. So I just divide by those numbers, and I get 0.37 moles of aluminum. Again, this will become very important moving forward. It may not seem more like busy work or something, but we're just getting you ready for what's going to be a lot more challenging later on. Our next example. Alright, let's say we started off with moles. So 6.80 moles of barium. And I want to know how many grams of barium that is. So you can see I put the unit and the substance. So whatever's on top goes on the bottom for units. We do our units first. And moles of barium can be related to grams of barium. There's only a few conversion factors. Unlike the non-metric conversions where it could be any number of things, there's like 3 possibilities here. So the 1 goes next to the mole because it's per mole. Barium, I got it written down here, 137.33 grams. So all of this lines up so I know what to multiply or divide. So when I do my units and my numbers, that sets up for multiplication and division. So I get from that calculation 933.84 grams. So again, just multiplying across the top, I don't have to do anything with the 1, and that's that. Let's look at one more example on this one here. So I have so many moles to atoms. So 17.8 moles of calcium to atoms of calcium. All right. Again, what's on top goes on the bottom. So moles of calcium on the bottom. And moles are related to atoms. They're related to particles as well. Atoms of calcium. And again, when this unit on top matches what we're trying to find, we're in the right spot. Now we just need to fill in our numbers. For every mole, which is why we put the 1, we have Avogadro's number, 6.02 times 10 to the 23rd. Now I'm going to show you how to use your calculator properly when we get back to class, but when we multiply this out, you get 1.07 times 10 to the 25th atoms. An unimaginable amount of atoms, but there's actually billions and billions and billions of atoms everywhere we have. So continue on. We'll see the rest of the examples on the next video. See you there.